right now, so you're now going to be on YouTube. But also, if you all ask me to do problems from the practice exam, those will be recorded separately. So I've got two copies of my recording software running right now. So you may see like when you do one of the practice exams or one of the problems from the practice exam, I will take your questions, I will respond to them, but I want to do it kind of straight through as a way to make the best recording for that. And then after that, we can kind of stop and discuss after I stop the thing that's going to wind up on YouTube as the solution to the practice exam problem. I see lots of folks joining. How's everybody else doing? Jazz says she's good. Good, Lisa. Glad to hear it. Yeah, Ryan, motivation is hard, right? This is a very different work pattern for everyone. Um, One of the things that I'm going to try to do, and I apologize, I've been a little bit harried the last few days, is every day send out an email to everybody, like telling you all what's coming up. Like, here are the things you need to do to stay on the ball for 211. So I hope to give you a little bit of structure. Kira, my family drives me crazy too when I visit them sometimes, but I love them very dearly. So I'm sure your family is very appreciative of you. But if there's anything we can do to help you, of course, let us know. So this review, I have no agenda for. Um, I have, I can put the practice exam up on the screen share and work through problems, or we can talk about big ideas. If you like, I could kind of do a concept review of the whole class, um, and then or the whole unit, like what did we do in Unit 3, and then start diving into problems that you suggest. But I think what may be more efficient is to dive right into doing sample problems, and by doing those, we'll see manifestations of the big techniques from our unit. So, what would you all like to do? So, Ryan, that's what you want to do? Okay. Um, so why don't we start with you all telling me what it is that you would like to talk about? Are there any sample problems you all would like me to work through? Okay, Martina. Yeah, that's what I was kind of hoping to do. Um, in part because then I get to make the the solution videos. Um, okay, yeah, I'm glad you found that useful, Ryan. That's the hope. That's why we do this. Um, one of the things. So I'm a performing choral singer, and one of the of course we rehearse and we all go sing on our own, sing together, and learn our music by performing it because the best way to give a good concert is to practice giving the concert. But we also like all listen to the music in our cars, and kind of hearing other people do the same thing and hearing how it goes is useful. So, what problem would you like first on the practice exam? Could you just go in order? Sure. Yeah, y'all just want to go through? All right. Let me share my uh, window here. Okay. Yeah. So, can I get before we start? Can I get feedback from the people here about how Friday's recitation went? This thing about turn up just at a different time of day to practice different problems. Did you all find that helpful? Okay. Yeah, I mean we've never done this before. I've never taught an online class before. I have no idea what I'm doing. Um, but to help us get better at it, um, we want your input on how this goes. Okay, there we go. My program is being weird. So you want to start with problem one. I'm gonna have to restart my handwriting program. Actually, it is acting a little bit funny. So give me one moment. I mean, so Derek, we told them explicitly they were supposed to help you. So if you could tell me which TAs did not get that memo, because that tells us which TAs were not coming to our staff meeting, that will be very useful. Because then we can say, hey guys, you should have known this. Oh, I know what's wrong. Now we're good. Okay, so you wanted to start, now that my tablet's working, right? With the very first problem. So this is one of Professor Rudolph's questions. Can you all see okay? Okay. Does anyone know where the answer key for practice exam 3 is? We are making it right now. So what I write right now is going to wind up on YouTube. So I'm now going to start recording on my other recording studio. Actually, it is set up a little bit funny. Stand by for one moment. I'm sorry. I'm running a pretty complicated recording setup here. There we go. All right, so this is question 1 on the practice exam. So here you're dragging a sled over some icy snow. You're pulling with a force that is directed above the horizontal, like we often are. And we know the coefficient of kinetic friction. So I may clear my throat or cough a bit. I'm not sick. I just had some very spicy Szechuan food for dinner. So here's the sled. It's being hauled by a rope like this, and we have a person, very long body here holding the rope. The tension force is 8 newtons. So this problem is sort of starting like one of our free body diagram problems, except here we're going to be using our knowledge of forces to calculate the work that they do. So we know that in the beginning we are here. So at this position, I'll call this A. And we're going to move over to B, which I'll draw in a moment as soon as I figure out how to hold my stylus. So we're going to wind up over here at B, which is separated by a distance. Come on. A distance of 4 meters. So what I'm going to do now, we're going to need to calculate the work done by these forces. So I'm going to go ahead and do a little bit of trigonometry on my free body diagram. So here is our object, our sled. We have a couple of forces that act on it. I've got to switch my layout here. So the tension force goes like this. Now we're going to need to decompose that into components, which is fine. We know how to do that. We're old hat at that. Ty, that's theta. Ty is t sine theta. Tx is t cosine theta. We have some other forces too. We have the weight of the sled. We have the normal force going upward. And finally, we have kinetic friction going backwards. While I'm talking, by the way, feel free to ask me questions. I will answer them live. Whoops. Wrong tool. Now, we're going to need, so I'm going to leave that here. So there's our free body diagram. I will need to determine how big the force of friction is. I'll need to determine the normal force for that, but we'll do that as part of part B. So part B says calculate the work done by these forces. So let's get started on that. So the work being done by tension is the force of tension dot product with the displacement, which is, so the definition of the dot product, remember, is the size of the force times the direction displaced in the direction of that force, the distance displaced in the direction of that force, or the size of the displacement times the component of the force in the direction of the displacement. So I'll write that as the displacement here, which is just d times the tension force component that is parallel to that, which is dt times dtx, which is dt sine theta. The work due to friction, we're going to have to think a little bit harder. Just because we need to know how big the normal force is. So that's the force of friction, dot product with the displacement. Now notice that these are anti-parallel, so that just brings down a minus sign. So that's going to be, some of you like to think of work as work is force times distance times the cosine of the angle between them. But here, the displacement is to the right, the force of friction is to the left, so the angle between them is 180 degrees. Thank you, people. You're pointing out that I messed up. This is what happens when I do physics when I'm tired, and I rely on students to keep me straight. So yes, the horizontal component is cosine. Thank you. Thank you so much for correcting me. I didn't just genuinely mess that up. So here, this is going to be minus the force of friction times d, which is minus mu times the normal force times d. So we need the normal force. So let's find that. In y, we know the sum of the forces in the y direction is 0, because this thing doesn't move up or down. Yes, Andy and Martina. So I am very tired. If I make mistakes, if there's something where you think I have made a mistake, I have probably genuinely made a mistake, because I can't talk and do algebra at the same time. So please call out my mistakes and I'll fix them. In y, sum of the forces is 0. So that tells us that the normal force minus mg, here I'll get this right, plus t sine theta is 0. So solving for all of this, this means that the normal force is just mg minus t sine theta. And that's kind of what you expect, right? The normal force is the weight of the thing minus however much you're helping support it with the rope. So now we can finish this. We know that the work from friction is just mu d times all of that stuff times mg minus t sine theta. Okay, so part C and D ask us to apply the work energy theorem here. So part C says, assuming the sled started with the speed of half a meter per second, what will be its final speed after the 4-meter distance? So here we use the work energy theorem. We know that the initial kinetic energy plus the work done by all forces, so work done by tension plus the work done by friction. Oh, forgot the minus sign in the work done by friction there. That's important. Because remember, that there is going to be negative. Equals 1/2 mv final squared. Note here, the normal force and gravity do no work. Since they are perpendicular to the motion. Okay, but we know what all of those things are, right? We can just substitute in. So we get 1/2 mvi squared plus the work done by tension, which we just wrote out up there, plus dt cosine theta, minus, remember the work done by friction is negative, mu d times mg minus t sine theta equals 1/2 mv final squared. So we're supposed to solve for v final. So doing that, that's just a matter of dividing through by 1/2 m. That gets us v final is the square root of a lot of stuff. That's the square root of v initial squared plus 2 dt. Whoops, I actually need a fraction here. 2 dt cosine theta divided by the mass. Remember, I'm multiplying by 2 over m minus 2 mu d mg minus t sine theta all over m. Now, you might say, oh, well, we want a number for that. Since I'm running 2 copies of my recording software, my computer is getting a little bit loaded, but we should be okay. So I'm going to type this into Google. So the initial velocity is 1/2 meter per second. So you can't see this right now. So I want the square root of 1/2 meters per second all squared plus 2 times 4 meters times the tension, which is 8 newtons, times the cosine of 30 degrees. Remember, if you're using Google Calculator, you've got to type degrees. The mass is 3 kilograms, minus 2 times the coefficient of friction. Coefficient of friction is real small here. It's 0.05. 2 times 0.05 times the distance, which again is 4 meters, times the quantity. All right, the mass is 3 kilograms times 10 meters per second squared minus tension was 8 newtons times the sine of 30 degrees, all divided by the mass, which was 3 kilograms, close parenthesis, and hope like hell I typed that right. So I get 3.9 meters per second. Actually 3.91 to 3 sig figs. So this may seem like it's not slowing down that much, but the coefficient of friction is only 0.05. So that's kind of what we expect, right? Note that mu is small. Let me go back to the collaborate window. Nobody has any questions. Part D says, after pulling, you drop the rope and get out of the way. How far will the sled slide before coming to a stop? So now the only force doing work is friction. So now our distance is an unknown, but that's fine. I can use the work energy theorem and solve for an unknown distance. I'll write that step down. Use work energy again and solve for the unknown distance, which I will use the symbol B for. B. So again, so here we're interested in it coming to a stop. So a stop means no final kinetic energy. So here the only force doing work is friction, right? Because we let go of the rope. So I have 1/2 mv initial squared plus the work done by friction. We already know how to calculate that. So the work done by friction is minus mu b times mg minus t. But this time there's no tension, right? So this time, in calculating the force of friction, right, the tension term goes away because we're no longer supporting it partially with the rope. So this was a bit of a tricky problem because you had to think clearly about how big the normal force and thus how big the force of friction was. And this is equal to 0. Now we'll note here that the normal force is now just mg since we dropped the rope. So solving for b, that's pretty easy. I can cancel the m's. That's good. I don't want to worry about that. This tells me that b is 1/2 vi squared over mu g, where v sub I here is just 3.91 meters per second from before. That's the velocity it was going when we dropped the rope. So if we do this mathematics, so this is a lot easier. We're just going to use the numerical value here. So I'm going to get 1/2 times 3.91 meters per second, all divided by mu was 0.05 times 10 meters per second squared. We use 10 for g. This gives me, oh, I must have mistyped my units. Yep. So folks, I want to show you something really interesting. I'm going to share my So this is a good thing to know. So folks, I expect that you will use Google Calculator to do calculations on your exam. That's fine. You may do that. I'm going to share. So for the people watching live on Collaborate, so look at my Google search tab. So I've typed in the formula, but notice that I was expecting a distance, but I got an answer in terms of time. I have messed up here, right? I forgot to square the velocity in the numerator. It is always a good idea to type in units when you're using Google Calculator, because Google Calculator is smart enough to do those units. And if you have messed something up in typing in the numbers, like I just did, Google Calculator will give you something that's not the units you expect, and that will be a red flag that you have, in fact, messed something up. So I'm going to switch back to sharing my writing software. So the answer that we got was 15.3 meters. And that is the answer to problem 1. So for the folks in chat, would you be able to use work equals change in total energy? Yes, that's kind of what we did here. Work equals change in total energy is exactly what this formula right here is. So here there's no sort of potential energy, right? The only forces doing work are non-conservative forces, the tension and friction. So here the only thing contributing to the total energy is the kinetic energy term. Oops. But yes, so normally the work done by non-conservative forces is the change in total energy. So total energy is just kinetic here. Any other questions about this problem before I move on? Okay. I'm going to stop recording for the segment that's doing problem 1 here. Actually, crud. I just realized that was, you know what? For the solutions to the practice exam, I'm just going to post the live recording of this session. I had something wrong on Open Broadcast Studio over here. So the live recording of this is just going to be the solutions to the practice exam, since that's what you all want to do. So shall we move on to question 2? Is there a PDF for the practice exam? Yes, there is. Stand by for 1 second, and I will get you the link. It's right on top of the course website, but if you're looking on Blackboard, you might not be able to find it. Ah, thank you, Grace. All right, let's move on to number 2. So number 2 is a very conceptual question. It's about the Newton's cradle. So this is the little thing where these balls bounce back and forth. We have one actually made out of bowling balls in Stolken Auditorium that's really cool to see. And unfortunately, we couldn't show you the one made out of bowling balls because you're all at home. The thing that we need to know for this problem is that these collisions are very nearly elastic. So that means, for elastic collisions, that means I need to get off my highlighter tool. That means I need to get off of my writing squares tool, that the initial kinetic energy equals the final kinetic energy. So in this problem, you're asked to look at several different ways this thing could bounce, and to answer why it is that it only bounces in one particular way and doesn't bounce in others. So since we're dealing with collisions, this tells us momentum is conserved. I'm so tired I can't even spell. And we also know that kinetic energy is conserved. So, let's start. So spheres A and B come to rest. Spheres C, D, and E begin moving to the right with a speed 2/3 v0 each. So what I'm going to do is, in the beginning, we need to know the initial kinetic energy and the initial momentum. So the initial kinetic energy is going to be 2, because there are two balls moving, both A and B, times 1/2 m v0 squared, which I'm just going to keep like that. I'm not going to cancel the factors of 2. The initial momentum is going to be 2 mv0. So here what we're going to be doing is we're going to be looking at the proposed final states and seeing if they are equal. We're going to just choose a coordinate system where that way is plus. So here, we'll do momentum first. So the final momentum is going to be 3 times m times 2/3 v0, because I've got 3 balls moving to the right at 2/3 v0, which is, well, cancel the 3's, 2m v0. So this proposed thing does conserve momentum. Let's look now at kinetic energy. So here we've got 3 balls going at 1/2 m times 2/3 v0 squared. Zoom in on that to make sure people can read it. Notice that 2/3 squared is 3/9. Excuse me, 4/9. And 3 times that is 4/3. So this is going to give me, well, let's see. So 3 times 2/3 squared is 4/3 times 1/2 is 2/3 m v0 squared. Actually, I am going to go ahead and cancel this here and just say that the initial kinetic energy is 2 times 1/2 mv0 squared, which is just mv0 squared. So notice, 2/3 mv0 at the end, mv0 squared at the beginning does not conserve kinetic energy. So the answer is no, kinetic energy not conserved. And all of the rest of this are the same method. So we're just going to repeat this a bunch of times. So here, the final kinetic energy is, so let's see, spheres A and B come to rest. Spheres D and E begin moving to the right at a speed v0. Sphere C does not move. Anybody who's ever seen one of these like happening for real, this is the thing that actually happens. Pardon me, I have something slowing down my computer. Give me one moment. I just want to see what's chewing up compute power. It looks like Collaborate is actually hogging my CPU power. 2 are initially amusing. Grace, let me go back to the thing to answer your question. Sorry about that. I was trying to make sure my computing stuff keeps working. So Grace says, isn't the Newton's cradle elastic? Why isn't energy conserved? That's the point. So the idea of this question is we're telling you that we're giving you certain outcomes, and we want you to tell us which outcomes are possible. So this outcome that we just looked at for the first one, this outcome, whoops, is not possible. So this is not what really happens. We'll see that in B, that conserves both kinetic energy and momentum, and that's the one that actually does happen. So here, the final kinetic energy is going to be 2 times 1/2 mv naught squared, which is equal to mv naught, big red check mark. The final momentum is 2 times mv naught, which is also a big red check mark. These are the same kinetic energy and momentum that we started with. So in this case, this scenario conserves both momentum and kinetic energy. This one is possible. This is the only thing, in fact, that happens when you play with one of these. Okay, so part C says sphere B comes to rest. Sphere A bounces back, moving to the left at a speed v0. Sphere E begins moving to the right at a speed v0. So here, this problem is checking to see if you understand that momentum is a vector that's moving to the left. So we're going to get a negative term. Oh, yes. Thank you, folks. We're going to get a negative term in the momentum. I forgot to write my square. Again, thank you so much, folks, who are catching my little typos. So let's see. We've got one going to the left, one going to the right at V0. So here, the final kinetic energy is going to be 2 times 1/2 mv0 squared. We've got two objects moving at v0. Remember, kinetic energy is not a vector, so it doesn't matter which way they go for the calculation of kinetic energy. But the final momentum is going to be mv0 minus mv0, because one of them goes to the right, one of them goes to the left. This gets a big red X. So this one is not possible. Momentum is not conserved. Okay, part D says spheres A and B come to rest. Sphere E begins moving to the right at a speed 2v0. So here, A and B come to rest. We've got one thing moving at speed v0. So the final kinetic energy is going to be 1/2 m times 2v0 squared, which is, remember, the 2 is squared here, right? This gives us 2mv0 squared. It turns out this one does conserve momentum. But this is not possible. Kinetic energy not conserved. This would actually be a rather remarkably frightening thing to have happen because energy seems to come out of nowhere here, right? We have more energy at the end than we started with. So unless someone has put gunpowder on the sides of these little Newton's cradle things, then that violates conservation of energy. Finally, we have the same result where one of them begins moving to the right at a speed 4 v naught. What happens here? So here the final kinetic energy is 1/2 m times 4 v naught all squared. 4 squared is 16, so this is 8 m v naught squared. Nope. Final momentum is m times 4 v naught to the right. Whoops. Which is 4 mv naught. Nope. So this one doesn't conserve either. Would you have to show both on the exam if you see one isn't conserved? No, you wouldn't. Here I'm being kind of especially thorough, just because I am like solving problems for everybody. For D, would the 2 need to be squared? Yes. Oh, yep. Thank you. Thank you. I put the square. I said the right thing, but I wrote the wrong thing, and that's actually super important. Yes, the idea is that there you're squaring the entire velocity, and the 2 is squared. That's the whole thing that makes that one not conserve kinetic energy. So thank you, Amanda. Any questions about this problem before we move on? Okay. So we're going to move on to question 3. So here we've got a thing sliding into a thing. They collide, they stick together, they then slide into a spring. So I'm going to label 3 moments in the motion. So A is right here. B is here. And then C is here. We don't really have much room to draw diagrams here, so I'm just going to write out what these represent. So A is at the start. B is right after collision. C is the spring compressed maximally. And the thing's not moving. So in this problem, we need to use different techniques to understand different moments in the motion. Whenever you see a problem where a collision happens and then something else happens, the big idea is to make sure you're clear on what techniques to use in what parts of the problem. So here, A to B, we're going to use conservation of momentum, since it's a collision. And here, as this goes from B to C, we're going to use work energy. So, what are the momentum and kinetic energy of the 2-block system just after the collision? So here we need to use conservation of momentum to understand what happens in the collision. Let me write that down. I'll say to find VB after the collision. So I've got initial momentum equals final momentum. That becomes, let's see, I've got M1 and M2. You know, for these, I noticed that there's a certain pattern in these masses. I'm going to call this 2m. I'm going to call that m, and m equals 1.5 kilograms. That way I've only got one mass variable that's going to be hanging around, and that will make my life simpler. I want a very simple life right now. So this means that, let's see, block 1 is a mass of 2m. 2m v naught equals, so after they collide, vb. So thus vb equals 2/3 v naught, which is 0.8 meters per second. I can do that one in my head. The kinetic energy, well, just to, follow the directions in the problem, I should say P final is, well, P final is P initial, right? 2m v naught or 3m vb. They're equal. That's the point. The kinetic energy after the collision, well, equals 1/2 times 3m, that's how much mass is moving, times vb squared. Let's see. So I'm just going to type this one into my handy dandy Google calculator. I've got 1/2 times 3m, so that's 4.5 kilograms, times vb is 0.8 meters per second, all squared, equals 1.44 joules. You'll probably notice that Professor Rudolph's problems, this is one of Professor Rudolph's problems, involve numbers a little bit more often than mine do. How far will the spring compress after the block slide into it? Well, here we use conservation of energy, right? Notice that from B to E, we're using the work energy theorem, conservation of energy. So here, the initial kinetic energy plus the initial potential energy plus the work done by other forces like friction equals the final kinetic energy plus the final potential energy. But I don't have any initial potential energy because the spring starts uncompressed. I don't have any work being done by other forces because the only force here is the spring. And I don't have any final kinetic energy because the thing is coming to rest here, right? We identified that there. So that means that 1/2 times 3m vb squared equals the formula for kinetic energy, 1/2 k d squared. We're going to solve for d here. So see here, d is, let's see, we're going to need a, so I can cancel the 1/2s, right? So I just need to divide by k and take a square root. So this is 3m vb squared over k, the square root of all of that. Now I've got numbers, so let me plug those into Google Calculator. I want the square root of 3 times the mass. The mass here is 1.5 kilograms. That's what m means. Times VB. which we decided was 0.8 meters per second squared, all divided by k, which is 4,000 newtons per meter. And Google Calculator has, it's not given me an answer. That's because I forgot to type in one of my units. So this is going to be 2.68 centimeters. Is momentum conserved with the spring? Really good question. Yes, Nicholas, you could use the kinetic energy you calculated in the last part. So yes, that numerator here is just, well, it's twice the kinetic energy because I multiplied through by 2. Yeah, Nick, you could certainly do that. I tend to like algebraic formulas rather than numbers whenever I can, so that's why I did what I did. So Grace says, is momentum conserved with the spring? No, but energy is. So remember, momentum is a vector. So here I'm going to make kind of an argument in words. So springs are conservative forces. So the kinetic energy once the blocks bounce back must be equal to the kinetic energy before contacting the spring. So this means two things. One of them is that the kinetic energy after the bounce must be equal to the kinetic energy before the bounce, which was, well, the number we found up there, 1.44 joules. And now this is the big one. The only way for the kinetic energy to be the same after the bounce is for the thing to come back at the same speed, right? So the momentum, well, we'll say it this way. So the velocity must just change direction but keep the same magnitude. So the final momentum is just going to be the initial momentum with a minus sign. Oh, my handwriting program crashed. Give me 1 minute to restore it. I need to share this again. So the final momentum is minus the initial momentum, which is minus 2mv naught. Any questions about that problem? Okay, let's move on to number 4. We're making pretty good time here. So this is one of my favorite problems ever. I give this in some capacity every year, although this year I built a snazzy new diagram for it. So the things that we need to know, gravity goes straight down. By the way, please type questions into chat as we go. I'm always happy to answer your questions here. As the swing moves from position A to position B, what is the work done by gravity? So the work done by gravity is equal to the force of gravity times the displacement, well, we'll do it this way, dot the displacement, which is the force of gravity times the distance moved downward. So to find the work done by gravity, I need to know the distance that I have moved downward. One moment, I'm setting my toolbars up to be in the spots that I want them to be. One second, it looks like we're in a little bit of danger of cutting something off the recording. So I'm going to just monkey around with Open Broadcaster Studio just a little bit. There we go. So that's just going to be equal to, well, I need to figure out how far I move downward. This is a bit of geometry that you had done before, but we'll do it again. So notice this blue triangle that I'm drawing in here. This is a right triangle. Oh, I need to turn off rotation snapping here. Here we go. So this side is L. Oops. This side is L cosine theta, which means this little piece down here, the piece we want, is L minus L cosine theta. You may remember doing that from your homework. So that means that the work done by gravity is equal to mg times L minus L cosine theta. Done. What is the work done by the wind? Well, the wind goes to the right. So here, the work done by the wind is the force of the wind dot product delta S, which is the force of the wind times the distance moved in the direction of the wind, which is right. Well, the distance moved to the right, conveniently, we can get from the same handy-dandy little right triangle. This is L sine theta. So that means that this is the force of the wind. What symbol did I use? Fw times L sine theta. So I noticed that people are not saying stuff in chat. I'm going to interpret that as either everyone is bored or you all are following. So are people following what we're doing in these problems? Okay. That's a good thing, right? I mean, it sounds like you all know what you're doing. And in many of my conversations with students over this last week, I found that I've had a lot of people say, hey, could you check my homework? And I look at their homework and it's like, oh, yeah, you understand everything. So it sounds like you all know what you're doing pretty well. So here we're finding the speed of the swing at position B. So here we're just going to use the work energy theorem. So the kinetic energy at A plus the work done by gravity plus the work done by the wind equals the kinetic energy at B. All right, we started from rest, right? So 0 plus the work done by gravity, which I found was mg times L minus L cosine theta. mg L minus L cosine theta. Plus the work done by the wind was plus Fw L sine theta equals 1/2 mvb squared. So VB, it's going to be the square root of a whole bunch of garbage. So that's going to be 2g L minus L cosine theta. Again, I'm dividing through by 1/2 m plus the force of the wind divided by the mass times L sine theta. All right. Now we need to write down an equation that you could solve for the angle phi in terms of all of this other stuff. Now here we've got a choice. We can either use the work energy theorem going from B to C, because we just figured out the velocity at B, or we can use the work energy theorem to figure out or to go all the way from A to C. We could do either. Both of them are kind of equally complex, right? You know, neither one's that complex. Just to make a point to students watching, I'm going to here use the work energy theorem from A to C, just to demonstrate that this is a thing you can do. Shouldn't it be 2 times yes? Yep, dropped a factor of 2. Thank you, Derek. So Derek points out that when I multiplied through by 2, I forgot to write a 2 there. Thank you. Let's make that a little bit neater. So here I've got the kinetic energy at A plus the work done by the wind plus the work done by gravity equals the kinetic energy at C. Notice that I'm not moving at A and I'm not moving at C. So this is pretty easy. Where did the work of wind come from? So Griffin, the work done by some force is the size of that force times the distance moved in the same direction. So the size of the force is F sub W here. And the distance moved horizontally is L sine theta, which is this value up here. You good, Griffin? Good. All right. So now the for F wind L sine blah blah blah, is that because phi is 90 minus theta? We actually don't know that. We have not yet figured out the work done by wind going all the way over to C. Okay, we're about to do that. So phi is not 90 minus theta. Phi is some other angle. And notice that this question says, write down an equation that you could solve for the angle phi. So we don't know what it is yet. The whole point of this part is to find it. So here, notice that, tool. Notice that, wrong tool again, sorry about that. The work done by the wind is the force of the wind times the distance moved in the same direction, which is x, which is the force of the wind times L sine theta plus L sine phi. And the work done by gravity, so looking back up here, I can do the same stuff that I did before. Over here, I can figure out this height between these two little dashed pink lines. This distance here is L minus L cosine phi. Same logic as before. So the work done by gravity is the force of gravity times minus delta y, so the distance moved downwards. We're going to get a negative value. That's fine. Equals mg times L minus L cosine theta minus L minus L cosine phi. The L's cancel, and this is just going to give me, whoops, forgot my, yes, that's right. So we'll actually do a sanity check on the sign at the end. This gives me mg times L cosine phi minus L cosine theta. Does this make sense? Well, phi is going to be a larger angle than theta, which means its cosine is smaller, because cosine is a decreasing function in the first quadrant. So this means that this overall work done by gravity will be negative. And that's what we expect here, right? Because we're in total displacing upward from A to C. So I've done a sanity check to make sure that my answers are right. So continuing this means that the force of the wind times L sine theta plus L sine phi plus mg L. You know what? I'm gonna run out of room. So we've got to. I'm gonna draw a little barrier thingy here, and just do this here. So that tells me force of wind times L sine theta plus L sine phi plus mg L cosine phi minus L cosine theta equals 0. And that's the answer to the problem. Remember, the question only asks you to write an equation that you could, in principle, solve. I'm not going to make you do the algebra here. E asks, when the tire swings back to the left, will it stop at position A? Will it move further? Or will it not come as far? So here, it's going to come back to where it starts, because when the tire reaches A again, the total work done by the gravity is the force of gravity times the displacement, times, and we get rid of these extra parentheses, Fg times minus the displacement in y, which is 0, because the displacement in y is 0. Same logic for the wind. Total work done by wind is Fw times delta x, which is also 0. So the total work from A to A is 0. So the kinetic energy reaches 0 at A, and it stops again at A. So the demo that I did in class with the bowling ball, if I did that with the wind blowing, right, if the wind had this property that it exerted a constant force, then it wouldn't hit me in the nose still. Um, does everybody understand this problem? Because this problem is probably the absolute most important problem for the work energy theorem. This idea here that calculating the work done by these forces is equal to the size of the force times the distance displaced in the direction of that force. Yes, Nicholas, this is exactly that. So what we didn't assume this, but what we've discovered is that the wind is a conservative force. And that shouldn't surprise you, right? Because gravity is a constant force downward, and we know it's conservative. The wind is a constant force sideways, at least in this problem, and it's a conservative force. So yeah, what we've kind of discovered is that the wind here is a conservative force. Could we please clarify again why? Um, so Jasmine, are you talking about part D or part E? Part D. Um, because at A, the thing wasn't moving. Here, the velocity is 0, and there at C, the velocity is also 0. So what that means is that the thing has no kinetic energy at either A or C. Well, work is the change in kinetic energy. So if the kinetic energy started at 0 and stopped at 0, the network must be 0. Jasmine, does that answer your question? Yes. Good. Griffin, how do you know when energy is conserved? So as a um, so here we've encountered two forces in this problem that we know are conservative, or in this class. One of them is springs, and the other one is gravity. And those you know are conservative because we've talked about them a bunch in class. But here we've encountered another force. We didn't assume it was conservative, but we discovered that at the end. And the definition of a conservative force is a force where if you travel along any path and come back to where you started, the net work done is 0. So I know that the work done by the wind is the force of the wind times the displacement index. Um, and that's the same whether I go to the left or go to the right. Yes, Demo, exactly. The wind will do negative work when the tire swings back. So if the tire swings to the right, wind is doing positive work. If the tire swings to the left, the wind will do exactly the same amount of negative work. I didn't write this here. I'll clarify it verbally. Um, but one of the ways that you know is if you have a force whose magnitude and direction, magnitude and direction don't depend on the direction you are moving. So let's compare the wind to friction. And this is getting to Grace's point. So if I imagine like an object sliding back and forth, friction changes direction when the object changes direction. So if I have an object sliding back and forth over a surface with friction, friction's doing positive or negative work one way and negative work the other way. So friction's an example of a non-conservative force because in a lot of situations it always does negative work. Air resistance is the same. So in real life, the wind doesn't apply a constant force, right? We saw it's gamma v squared, where v is the relative speed. So if you imagine a tire swinging in still air, so with no wind, then when the swing swings to the right, air resistance pushes it to the left and does negative work. When the swing swings back to the left, air resistance goes to the right, also in the opposite direction, again does negative work. So in this problem, we kind of waved our hands at the work done by the wind and assumed a simplified model. But that's not really true in real life. In real life, there's friction. There's friction in the rope. There's also the fact that air resistance is a little bit more complicated than what we assumed in this problem, and it will do negative work. So Grace, does that answer your question? Just we had a simplified model of a tire swing in this problem. Good. Um, so any other questions about this problem? Because this is, I think, one of the most important problems in this exercise set for understanding the work energy theorem. If you understand this right here, then you are in really good shape for the work energy theorem. All right, let's move on to number 5. This problem was on last year's exam. So trucks driving down steep mountains must continually apply their brakes to maintain a safe speed. I was on my bike today coming back into Manlius, and there is an 11% grade for like half a mile, and I was worried my brakes would overheat. I had flared my arms out. I had kind of puffed up my jacket. I unzipped my jacket so it would act as something like a parachute to slow me down to have air resistance do some negative work on me as well, and in doing so, reduce the amount of negative work that my brakes would need to do. You have a problem exactly like that on homework 11. Like homework 11 is like literally, I had a conversation with my cyclist girlfriend about that. Um, and like all of the problems are things that we worked through together. She wanted me to teach her the physics of cycling and the physics of some of this stuff. So we basically worked homework 11 together, and then like we had fun doing that. So I said, we're just going to write this up as an exercise set. Um, so write an expression for the total work done by gravity during the entire motion. So the work done by gravity, let me get on my right tool. The work done by gravity is, as always, the force of gravity times the distance moved downward. Remember, this is the force of gravity. This is the displacement parallel to the force. So how far did we move downward? Well, we moved downward we can figure that out by doing some trigonometry here. So that's a right angle. This distance is going to be L1 sine theta. Because this here is also theta by what a lot of people call the Z rule. Draw another right triangle here. And this distance is L2 sine phi. So the distance moved downward then is equal to L1 sine theta minus L2 sine phi, because we're going upward during the motion at L2. So the work done by gravity, I'll write that more neatly. Still learning to use the stylus, equals mg times L1 sine theta minus L2 sine phi. Okay, part B, write an expression for the total work done by friction during the entire motion in terms of mu, g, m, L2, and phi. Notice that there is no friction while the truck is on the road. So the truck's brakes have failed, so it doesn't have friction until it gets into the piece of the motion where we've put gravel and sand and stuff on the road to generate a lot of friction to save runaway trucks. This is a real problem. On the interstate, I believe it is I-90 coming out of the Rocky Mountains down into Denver, there's a huge descent of something like 6,000 feet over, I don't know, 15 miles, and um, trucks' brakes have to do an immense amount of negative work on the truck, right, to stop them from speeding up more and more and more. And if all of that negative work gets converted into heat into the car's brakes or the truck's brakes, and if the truck's brakes are not allowed or not able to dissipate heat faster than like heat is being poured into them, then the truck's brakes can melt and lose their coefficient of friction, lose their ability to stop a truck. And this happened a couple of years ago. There was a truck that actually lost its ability to brake because it was coming down this hill too quickly and killed a lot of people because the driver was arrogant. The driver didn't, he thought he could control the truck at this high speed and didn't use the runaway truck ramp. And this thing designed to solve this problem and kept going and like killed a bunch of people. It was really, really bad. So this is a real engineering thing. Um, Write an expression for the total work done by friction during the motion. Well, that's this piece over on the right. So the work done by friction is minus the force of friction times L2, because L2 is the part of the motion where we have friction. So here, this is just a minus sign, no trig, since here the force of friction and the displacement are anti-parallel. So here, the force of friction is mu times the normal force, which is mu mg cosine phi. That's the other angle. So the work done by friction is minus mu mg L2 cosine phi, where again that cosine factor came from the normal force. Could have been less enthusiastic than I normally am about color coding things, so I'll mark it there. Write a statement of the work energy theorem, conservation of energy, in terms of all of the stuff that you could solve for L2. You do not need to solve it. So, again, we're trying to spare you some algebra. So here, the kinetic energy. Why is no trig again needed? So Grace, there's no trig needed because here, let me draw a few arrows to make this plain. So we'll put it up here. So here, this is your displacement vector. There's your force of friction vector. They're just in opposite directions. So if you prefer to think about the dot product as A dot B equals AB cosine theta, that's the angle between the two vectors. So here theta is 180 degrees. And cosine of 180 degrees, not 18 degrees, I'm tired, is minus 1. So some students prefer this. Many students prefer to think of the dot product as force times displacement times the cosine of the angle between them. If this works for you, like great, do it, right? For some reason, this seems more complicated to my brain. I just think that the work done is the force times the displacement in the direction of that force. And here we are being displaced in the opposite direction of that force, and opposite means minus 1. Of course, Grace. Like this is why we let you ask questions, right? This is why we encourage you to ask questions. Um, I wish that I could like just sit down with everybody and have you do this, and you ask me questions as you do your work. You got that chance during recitation. Um, so yeah, if you ever want me to draw something to clarify it, right, that's the best use of, I'd rather do what you tell me to do than just do the problems. So continuing on where we were, um, work energy theorem says initial kinetic energy plus the work done by gravity plus the work done by friction equals the final kinetic energy, which is zero because the whole point is to bring the truck to stop. So we know V naught, right? We know that the truck was headed down the hill at a speed V naught. So I have 1/2 mv naught squared, and here I'm just going to copy the stuff I just figured out. So the work done by gravity was mg times L1 sine theta minus M2 L2 sine phi. The work done by friction was minus mu mg L2 cosine phi, and that equals 0. So there's your equation. Any questions about that? All right, so problem D is this idea of calculating the power from forces. So if we want to maintain a constant speed, this means that the power from the brakes must be equal to the power um, from gravity. So, so I should switch to my writing tool. So if the velocity is constant, the net power equals 0, and the power from the brakes equals the, we'll write it this way, plus the power from gravity equals 0. So the power from gravity is the force of gravity dot the velocity equals the force of gravity is mg, the component of the velocity in the direction of the velocity is going to be v sine theta. Remember, this is f grav. This is the component of the velocity parallel to it. So mgv sine theta, now I need to type this into Google Calculator because the number here is interesting. So m is 10 to the 4th kilograms, that's kind of what a truck weighs when it's loaded, times the velocity of 15 meters per second, times the sine of 10 degrees. Oops. I didn't multiply by g. I got the wrong units in Google Calculator for that reason. And I get an answer of 260 kilowatts. Exclamation mark, exclamation mark, exclamation mark. This is about 320 horsepower. That is a vast amount of heat being pumped into that truck's brakes. And notice 15 meters per second is not that fast. That's like 30 miles an hour. Imagine if the truck were driving faster. Brakes cannot absorb that much heat. They can't dissipate heat fast enough, and going down that hill into Denver, they will overheat, and the result is pretty bad. Any questions about this problem? All right, let's move on to question 6. Part A of question 6 was on last year's exam, and it kind of messed students up a lot. uh, these sorts of answer in words conceptual questions are very important. There's going to be some on this exam coming up, and take them seriously. Just because there's no math doesn't mean there's no physics. Lisa can attest to last year. She took Astronomy 101 with me, and we had, there was no math on any of the exams, really, but the physics was substantive. There was actually a lot of physics in Astro 101, and the exams were pretty challenging. I think the only math you had to do was like add small numbers for the uh, energy level stuff. So, explain why this must be true by invoking the work energy theorem. So what I'm going to do, I'm going to draw a few arrows here. But first I'm going to write some words. Let me read the problem first. So basically the idea is that at aphelion, the velocity is large, and at perihelion, velocity is small, and at perihelion, the velocity is large. So an object's kinetic energy and thus its speed increases if positive work is done on it. So here, the force of gravity points toward the star at any given point. So let's choose a point up here and label this. So here, the force of gravity points inward. At that same point, oops, get my arrow tool. At that same point, the displacement vector, the vector tangent to the motion, is like that. Notice that those are broadly in the same direction, right? If you prefer work equals force displacement cosine theta, notice that the angle here is less than 90 degrees, so it has a positive cosine. But really, the logic can be made simpler than that. The force of gravity points toward the star. We are moving closer to the star. Thus, the work done by gravity, and thus the change in kinetic energy is positive. As we move from aphelion to perihelion. Part B argues if you look closely at the star, you will observe that it is also moving slightly, with its center tracing out a small ellipse. So the way this thing will actually move, the star will dance around. It will move, in fact, opposite to the motion of the planet, like so. And I haven't said like argue based on any particular principle. I've just said argue that it must behave that way. And this is like the only problem I think we've done where momentum is conserved, but it's not a collision or an explosion. So here, there are no external forces. So momentum is conserved. So any change in the velocity of the planet must come with a smaller change in the velocity of the star so that the net change in momentum vector is 0. That's one argument. That's kind of the argument that I had in mind. But another argument that would be perfectly fine would be to invoke Newton's third law and to say the sun's gravity pulls on the planet. The planet's gravity must also pull on the sun with an equal force in the opposite direction. And the force pulling on the sun, yes, indeed, makes it move. Any questions about that? So which way does the planet move? So what I'm going to do, I'm actually going to show you. So I'm going to take a bit of a digression here, and I'm going to instead share a tab in Google Chrome. And now I'm going to go to the website for the Astronomy 101 class from last year, and I'm going to fire up an orbit simulator that I wrote. Now, the code, what you're looking at is code in the computer programming language Python. Yes, you all can see that. So we'll make it full screen. Let me make this text a bit bigger so we can see better. Now, the simulation code in here ought to look real familiar. We calculate the distance the planet is from the star by looking at the magnitude of the difference in their positions. We calculate the direction from the planet to the star. Hat here means direction, like I hat, J hat, K hat. We calculate the force that the planet and star exert on each other. Then we calculate the acceleration that results from that force using F equals ma. And then we imagine figuring out how they'll move in a very small interval of time. Remember that scene from Hidden Figures that we saw where Katherine Johnson invokes the Euler algorithm? This is the Euler algorithm that you're looking at here. We update the velocities of both the star and the planet by saying change in velocity is acceleration times interval. Change in position is velocity times interval. So here, I'm going to make the planet's mass, we'll say 1/20th of the star's mass. So we have a star that's only 20 times bigger than a planet around it. And when I click run here, the computer is going to evaluate this Python code. It's, in fact, what you're seeing down in the bottom is a verification of what we figured out from the work energy theorem, right? We figured out that the planet must move faster, so its speed is higher when its distance is smaller. And that's what we just argued based on the work energy theorem. But you'll notice here that the star is actually moving a little bit. That's because, and it's moving opposite to the planet, right? So remember, conservation of momentum says that when one thing goes up, the other thing has got to go down in order to keep the total momentum constant. So the star actually wobbles opposite the way the planet orbits around it. Let me click back to chat. Martina, does that make sense? Good. I teach an entire class on how to make simulations like this, where like writing something like that is homework. So it's Physics 307 taught in the fall. That's kind of one of my other classes. And I find these sorts of computer simulations a great way to learn physics. I'm actually going to change Physics 211 next year. So next year, Physics 211, starting from week one, is going to involve a whole lot less algebra and a whole lot more writing Python code. So you'll be solving these problems not only by doing math with pen and paper, you'll be having a computer do mathematics with you as well. And the advantage of that is you can actually see what's happening in real time. And if there's something going on that's funny with your computer code, you'll say, ah, it's not supposed to move like that. All right, let's move on to question 7. I have to scroll in my thing here. All right, so here, this is a fairly complex problem. Nicholas, coding, when you say coding is a nightmare, what are you basing that on? Like, what have your nightmares in coding been? While you're typing, um, MATLAB. So I have found that so I teach the programming language C in my class, and I found that both C and Python are pretty good beginner languages to start with. Um, they are C has a reputation for being hard. It is not. The reputation of C as a difficult language to learn is completely not a thing in all of my experience teaching students to program. And um, it turns out that you don't actually have to know a bunch of fancy computer stuff to make a computer do really cool simulations. So we actually don't dive into like really crazy computer science stuff. We learn just enough programming to be dangerous and then spend our time thinking about cool physics rather than doing, like how does the Linux kernel work? My answer to that is very well, but I don't understand it. All right. So this problem says we've got a mass that is compressing a spring. It shoots over here. We'll say that it shoots over here with some velocity a. Well, we'll say b for a reason that um, will become apparent in a moment. It collides here, and then both of these things slide this way, and then they hit the spring over there. So what I'm going to do is draw a couple of diagrams representing different stages in the motion. Um, Again, clear pictures are super, super important in these sorts of complex problems where you've got a collision and other things happening and you're using a combination of work energy and momentum. Clear pictures are the absolute best thing. So I'm going to take some time and draw really good pictures here. So the very first thing that I have is this thing is here. We have a coiled and compressed spring. This goes over here. Got a wall on that side. I have a coiled and compressed spring. I have my box M1 over here. And I'm going to say this is compressed by how much? Compressed by a distance d. The other block is just chilling here. And we can't forget the patch that has friction. Meanwhile, the spring on the other side is relaxed. I'm going to call this picture A. So I should label here M2 is not moving. So that's the beginning. Picture B I've again got the wall here, but it has shot the thing off. So this spring here is relaxed. This spring there is relaxed. And my object is just about to collide with the other one. The collision hasn't happened yet, but let's label this M1. Oops, M1. Bloop. Its velocity is VB. This one is still not moving. Come on, stylus. V equals 0, and now I have to put back the thing that I accidentally erased. Again, I'm taking the time to draw good pictures because that helps a ton with this. So that's picture B. Now, from A to B, I can use the work energy theorem to relate these. Because in the motion, I don't know or care about time, and I can account for the work being done by all forces, right? I've got friction, I've got a spring. Scenario C is right after the collision. Because remember, I'm going to need to use conservation of momentum to understand these collisions, but conservation of momentum cannot help me understand things like springs, right? The springs do not conserve momentum because they are attached to the walls. There's an external force going on here. Here's my little spot of friction. So now the two of these are stuck together. So right after the collision, here, both are moving at VC. And since these are the two diagrams that take me from right before the collision to right after, I can relate these pictures with conservation of momentum. Alrighty, now D. This is the ending one, right? Notice that the description of the motion is it propels it down, it hits the other spring. And all of these questions get to that. So I'm kind of like writing down the diagrams of everything that's going to happen in the motion. I haven't waited to see exactly what the questions are because I wrote them and I know what they are. You know, you might, as you're working the problem, come back here and draw these diagrams. So here this one is again relaxed, but this one is compressed, pardon my art, so we're, whoop, wrong tool. So this one is compressed by B, and here these two things are not moving because they've compressed the spring by its maximum amount. And again, to get from picture C to picture D, I'm just going to get rid of those words and put them somewhere else. This is work energy. This is compressed by B. All right, so now let's actually do the math. Now that we've diagrammed out the motion, all of this stuff ought to seem super obvious, or at least super straightforward. How fast is the first mass moving right before it collides with the second block? Well, that's just go from picture A to picture B. So here, use work energy from A to B. So here I'm going to use the ideas of potential energy because I've got a spring and I don't really feel like doing an integral right now. So I've got the kinetic energy at A plus the potential energy at A. I'm just changing colors here. Plus the work done by friction, which is the other force, right? The force that I don't associate with a potential energy, equals the kinetic energy at B plus the potential energy at B. But a lot of these things are zero. We are not moving at A, and there's no potential energy at B. So, doing the mathematics here, I've got the wrong tool. Boop. So I have 1/2 kd squared. The work done by friction is minus mu mg. How big is the friction-y patch? Oh no, the friction-y patch has a width b, so that means I can't use b here because the letter's already being used for something else. I'm going to use d2. So the work done by friction is minus mu mgb. Force of friction is mu mg. Distance moved against it is b. And this is equal to 1/2 m1 vb squared. So solving for all of this, this tells me vb is going to be the square root of, again, I'm multiplying by 2 and dividing by m. That should be m1 here. So that's going to give me k over m d squared from the first term minus 2 mu gb. So that's that bit. Any questions and or have I messed up my algebra? Okay, how fast are the two masses moving right after the collision? Well, here we use conservation of momentum from B to C. So let's see, I've got one thing moving in B. I've got two things moving together in C. So that's going to give me m1 VB equals m1 plus m2 VC. So VC is m1 VB over m1 plus m2. Alrighty, so now we do the next one. What is B again in part A? So B is the width of this little friction-y patch, which I'll draw over there more clearly. That distance there is B. Thank you for your question, Nicholas. So here we're just going to, again, use work energy from C to D. So I've got the kinetic energy at C. Notice that both of them are stuck together here. Vc squared plus plus the potential energy at C plus the work done by other forces, both of those terms will be zero, I'll cross them out in a moment, equals the kinetic energy at D. I'll go ahead and write the term out. Equals 1/2 kinetic energy at D plus the potential energy at D. I'm kind of changing my mind about notation on the fly. Because the spring is relaxed at C, there's no friction here, and we're not moving at D. So I can cross out a lot of these terms. And I get, keep forgetting to get off my arrow tool whenever I use it. This gives me 1/2 m1 plus m2 Vc squared equals 1/2 k d2 squared. So d2 is going to be equal to the square root of, I can get rid of my 1/2s on both sides. That's going to give me m1 plus m2 over k times Vc squared. We'll make the square root sign the right size, where Vc is given above. You can always do that, right? If you don't want to just do a stupid menial substitution and waste ink or space, just do that. When I was taking my graduate qualifying exams, I had two disgusting algebraic expressions, and I decided that one of them would be smiley face and the other one would be frowny face. And I got to my final answer, and my answer was a thing with smiley face and frowny face in it, and said, these as given above. I was kind of punch drunk during my PhD quals, right? I'd been working very hard, so smiley face and frowny face made it in there. All right, this is the last problem on our practice exam. So I've got two cars driving down the road. One driver falls asleep and bonks the other car. So what do we have? We have, the cars are going to be big blobs. So this car is going that way. This car is going that way. We know this angle here is 20 degrees. And then afterwards, I have two cars stuck together, two drivers that are probably very angry with each other, or rather, a wake driver that's very angry at a sleepy driver. They're stuck together, and they're both going to be moving some other velocity, v final, and we don't know what that is. Because I don't like numbers, they make me break out in calculators. I'm going to call this v naught. I'm going to call this theta. I'm going to call this m, although it'll cancel from the end. Demo, you said 20. Were you referring to the angle? Okay, yeah, 20 degrees. So, what fraction of the initial kinetic energy is lost? So, remember that inelastic collisions dissipate kinetic energy. So, I'm just going to write that down. This is an inelastic collision because things stick. So, kinetic energy is lost. Oh, I didn't finish part A. I just drew diagrams. So we'll get rid of that. And we're going to put a big arrow down here and say that for part A, momentum is conserved in x and y. So in x, I've got I'm going to color code green and blue. So for green car, I've just got mv naught. It's traveling in the x direction, so there's no trig. This car is going m v naught cosine theta. And then afterwards, the two of them are stuck together. So that's 2m v final x. So the m's will cancel, right? They've got to. And this tells me that v final x is going to be well, I just divide the other stuff by 2, right? v naught plus v naught cosine theta over 2. So here I'm going to use my handy-dandy calculator machine. v naught was 100 kilometers per hour. That's a hell of a speed to fall asleep at. 100 kilometers per hour plus 100 kilometers per hour times the cosine of 20 degrees, all divided by 2, is Google Calculator is giving it to me in meters per second, so I can write in kilometers per hour. So this is 97.0 kilometers per hour is the answer I am getting. Which is very close to 100. Right? So this sideswipe collision did not reduce their speed in the x by all that much. And I look at my math, and I did indeed do it right. So then in y, I do the same thing. I'm going to, again, color code the two cars. 0 plus mv naught sine theta equals 2mv final y. So So then v final y is going to be, well, my m's cancel, like I suspected they would. So this gives me, I should go back to black, v naught sine theta over 2, which is 100 kilometers per hour times the sine 20 degrees over 2 in kilometers per hour. Google Calculator says 17 kilometers per hour. 17.1, who cares? 1 kilometers per hour. So we want magnitude and direction. So I've got my two numbers. So for magnitude, I use the Pythagorean theorem. The magnitude of v final is the square root of 97.0 squared plus 17.1 squared kilometers per hour, which is, and now we go to our fancy calculator here. And this gives me 98.5 kilometers per hour. And for the direction, I should probably label a coordinate system, right? So a little bit better at drawing this. I'm kind of using this one, right? I'm letting downward be positive y. That's fine. So for direction, call that angle phi. Phi is arctan v final y. Oop, touchscreen glitch. 1 second. Over v final x, which is, going again to Google Calculator, arctan 17.1 over 97 in degrees. Don't forget that Google Calculator uses radians by default, and that gets 10 degrees. So, what fraction of the initial kinetic energy is lost? So notice we have gone from 2 cars at 100 kilometers per hour to 2 cars at 98 kilometers per hour. So I will, just so I'm not messy, I will say for part B, to see the next page. Bloop. So the kinetic energy is proportional to v squared, right? Both cars always have the same velocity. They were both going at the same speed, well, the same speed. Both cars were going at 100 kilometers per hour before the collision. They were both going at 98.5 kilometers per hour after the collision. So the initial kinetic energy is proportional to 100 kilometers per hour squared kinetic energy final is proportional to 98.5 kilometers per hour squared. I'm doing this basically to avoid having to do numbers. So the fraction of final kinetic energy over initial kinetic energy is equal to 98.5 squared over 100 squared, which I believe by Taylor series ought to come out to about 0.97. But I'm going to do it anyway. 98.5 squared over 100 squared gives me 0.970225. All right, everybody in chat, you're probably wondering how I did that so quickly in my head using Taylor series. I don't want to get into that on the recording because that'll sidetrack us. But in your Calculus 2 classes, Calculus 2, you do all kinds of stuff, and then right at the end of Calculus 2, you do Taylor series. And often this is presented in a way where it doesn't seem like it's important. Taylor series are the most important thing you will learn in Calculus 2, even though they don't seem like it at the time. So file that away as just, here is a thing we are doing. Maybe it is boring and dull and I don't see the way to do it right now. It is an invaluable way to calculate things quickly, whether you are doing algebra, whether you are doing numbers in your head or your programming computer. So keep that in mind. So this is 0.97. So this tells me that 3% of kinetic energy is lost. And we expect some to be lost, right, because it's an inelastic collision. So that brings us to the end of the practice exam. We went through this entire thing in 2.25 hours, answering your questions, talking through everything. This was 8 problems. The real exam likely will be, of course it's going to be shorter than this. It's going to be 4 questions with 2 short answer questions after it. 1 on the process of science, 1 on conservation of energy and momentum. So you don't get scared by a 24-hour exam, right? That just gives you lots of time. You'll be able to finish this exam quite quickly. What else would y'all like to talk about? I'm going to, at this point, save what I've done here. I'm at this point just going to chill here until somebody tells me to do something else in chat, because this technically was going to go until 10:30. Feel free to unmute your microphones and say stuff, or type. Shining asks, will there still be any time for us to ask questions before the exam? Yes, there will. So tomorrow I'm going to be putting the exam together. I'll be in front of my computers all day, so if you send me messages either on email or Discord or somewhere, I can help you. But Tuesday morning, we will be holding class, and class will just be an opportunity for you to ask questions. So we'll be on Collaborate from 9:30 to 12:30, just taking your questions. Lisa. Ryan has a question about homework 11. So before we get to that, I want to take Jasmine's question about 1E. So let me scroll up to that. So your question is, what was the normal force before? So here, this is the one where the person is pulling the sled, and they're pulling it up at an angle. So you did a bunch of this in Unit 2. The normal force here is whatever is required to stop the thing from falling through the floor. So if I just have something sitting on a table, the normal force will be equal to its weight. because there's no other forces in the vertical direction. But here, we are helping to support the thing against gravity from the vertical component of the tension. Um, so the y component of the tension reduces the normal force because I'm like holding it up a little bit. So when we computed the normal force here, it was mg minus t sine theta. And then when we calculated the force of friction, or the work done by friction, notice that the work done by friction was the coefficient of friction times some stuff that had mg minus t sine theta in it. Jasmine, does that answer your question? Sure. Brian asks, in question 5, part D, the one with the truck going down the hill, um, is that the extent of what you will have to do with power? Maybe, maybe not, because so that question came from last year's exam when we didn't have a whole lot of homework about this. Here you had those homework questions about the bicyclist riding into air drag, which I definitely feel in my legs today. And uh, because we did a little more of that this year, you might see something a little bit more sophisticated, but Brian, not really. Like power is a minor topic on this exam. You're not going to have to do something super complicated. If you were able to do question 5 part D, then you are fine. Just the idea that power is the dot product of force and velocity is all you need. Any other questions? See you later, Martina. Thank you for all your hard work and enthusiasm. Say hi to your bunny for me. Thank you, Jazz. Any other questions from anybody? Right, I'm going to stop the recording here, just because most people are probably interested in the solutions.